Welcome to this introductory video about the highlights of our newly released BESA Research 7.1. We will walk through some typical scenarios hands-on to show the benefits that can make life easier and maybe give you new insights into your data. We will particularly look at the boundary element model integration, confidence limit display in the individual MRI, multi-slice view of source images, combined MEG-EEG source modeling, improvements in the Bayesian Sesame method, and finally creating source montages from atlas regions. Let's start with our 3-shell BEM model applied in a clinical application scenario. This is a dataset with inter-ictal epileptic spike activity. 20 spikes were identified by pattern search and automatically averaged. The map sequence shows a pattern that hints towards propagation over time. We have calculated finite element and boundary element models. So let me now load this into source analysis module. I'm using a generous baseline and a forward filter for high pass to prevent compromising onset activity with later propagated activity. So now let us find the generators in this data, which was kindly supplied by Dr. Stefan Romp at the University of Erlangen, Germany. In source analysis, the individual finite element model is selected by default. Now I will first show the anatomy. On the left side, I see the PCA analysis of the EEG data. There are two fast components. I will try and model the fast components with dipoles. So let's mark the onset, then place a dipole and fit. It fits to the frontal lobe. Let me now see the residual and mark the residual activity. I can fit this with a second dipole. And let me now compare this with the boundary element model. I can switch off the FEM sources and switch head model. Then start modeling with BEM, which I can define in the head model box at the top. Now I can fit again using the boundary element model. I can steal the fitting interval from the first source by briefly reactivating the first source and then using this interval for the new source. Then fit it. And the same for the second source. So now I have done the same source modeling in finite element model and boundary element model. How about the confidence limits of these sources? Looking at the view in the individual cortex, I can see the two sources fitted with the BEM model, and also the confidence limits are displayed in the current slice. I can switch the confidence limit display on or off with the toolbar button here. Note that these ellipsoids describe the 95% confidence limit based on the noise statistics, but they do not incorporate other errors like modeling or co-registration errors. Now I can switch the FEM sources back on to compare the location of these sources. In this case, the confidence limits do not longer make sense because I have sources from two different modeling modes, so I will switch them off here. But I can now see how far apart the primary sources are. The bottom toolbar shows me the location in M&I coordinates. In the transverse plane, they are very close together, but the depth differs by about 13 millimeters. Now let us look at the MultiSlice view. I can perform a Clara analysis of the data using the onset interval that I used for fitting the first source. Here is the result. Going to the first Clara maximum, I can see that it is very well aligned with the dipole solution. Now I can toggle through the viewing options to get to the slice view to show the results in the whole brain. Let me switch to the sagittal view and then change the slicing options for the first slice to last slice and the interval. Now I can see where the activity begins and how far it spreads through the slices. Now let us move to combined EEG modeling. This is a combined MEG-EEG recording of inter-ictal epileptic spikes in a child with 122 MEG and 33 scalp EEG channels. Let me send this one to source analysis. Two generators are prominent from the PCA, at least in the EEG, and I have chosen an age-appropriate template model of a 12-year-old child. Let me first check on the baseline. If I make the baseline too large, then I get a red color indicating that it stretches into signal of interest. So I will move it back somewhat until I have a good baseline definition, and I can define the onset interval such that the first component explains as much data in the interval as possible, here 99%. Then I can place a dipole and fit. This is my EEG onset source. Now move to MEG. I will use the same interval, but a new source. The fit result is slightly different. And finally to MEG. I can see the modalities EEG and MEG gradiometers. Now add a new source, switch off this one and fit again with the same interval. I need to invert the source direction since the positive current should flow upward, and now I can compare the three sources in the anatomy. Can see the difference in localization. My EEG source localized a bit deeper. The MEG and MEG source localized in almost the same location. However, it is noticeable that the orientation of the MEG source resembles that of the EEG source. For MEG only, we lose the radial orientation component, so the orientation gained with MEG is more reliable. To a slightly different topic now, Bayesian source estimation was improved vastly using hyperpriors. This dataset is an evoked field, a visual motion stimulus recorded with MEG. I will send the relevant data segment to source analysis in order to do Bayesian source analysis on this. If I look at the global field power plot, I can see two peaks. The second is due to the motion processing, so I am interested in analyzing this one. I now have options in my settings dialog to use hyperpriors for modeling source strength, and I can also switch from automatic number of iterations to a fixed number, for example to 100 iterations. And I will start the Sesame with this set of options now. I will fast forward this a bit. Now I am done. And I can now explore the maxima. The first maximum is here in the right visual cortex, and I can check in the atlas and see that this is the V5 area, so definitely a vision motion related activity. I can see the source for this, and there are other maxima that I can browse through and see solutions. So I can easily create a new solution and check the time courses of activation. Finally, let us look at the atlas-based source montages. For an EEG data file, atlas-based source montages are simply available from the Source Montage button. Press it twice to get the submenu, then select the Atlas montage from the submenu of choice. I can check on the source configuration in the Montage editor if I like. For an MEG data file, atlas-based source montages are defined in the source analysis module. If I have a beamformer solution, I can even define a beamformer virtual sensor atlas montage. I just go to Open Solution, choose the Montage folder, go up one folder, and then into the Atlas folder. The solutions with BF are the beamformer solutions. Now I can apply this solution to the raw data by saving it as a source montage. It has been applied, and I can now browse through the data with the beamformer virtual sensor montage. And this concludes the introduction. Thanks very much for watching, and please look also at our other YouTube channel videos.